So now let's discuss about the activation temperature and enthalpies of different phase changing materials. So I'll do the graph first. So on our x-axis there is melting temperature in degrees Celsius, and on y-axis we have thermal conductivity. Thermal conductivity in log measurement, and it is in okay. So it's watt per meter Kelvin. So let's represent our organic materials, basically organic phase changing materials here in triangular format. And I will represent inorganic material by in circular format here. And metallic materials by square format here. So basically, in the plot, we had different classes of the PCM material with their range of heat of fusion. So we can notice that the organic material has quite low melting temperature as they are polymer but have high heat of fusion. So basically for organic materials, we have heat of fusion around 200 to 220 kilojoule per kg. For inorganic material, we have heat of fusion around 150 to 500 kilojoule per kg. And for metallic materials, we have the heat of fusion around 50 to 600 kilojoule per kg. So for organic materials, we have high heat of fusion. Now in case of metals, the temperature is quite restricted, but pure aluminium has been used as PCM material. Pure aluminum material has been used as a PCM material. So we have more continuous temperature range and we have high thermal conductivity for the metals. Now inorganic materials like salts, this is our inorganic materials. This is our metallic materials, and this is our organic materials. So for inorganic materials like salts, they have low melting temperature, but we have same salts that are used in concentrated solar power plants that can work approximately at 500 degrees Celsius. So we have problems related to the stabilities, degradation, interaction within the container, and so on. I think many of the people have a doubt, like what is the heat of fusion basically? So we can define the heat of fusion. Heat of fusion. This is the amount of heat energy. This is the amount of heat energy required to change a substance from a solid to liquid at its melting point without changing its temperature without changing its temperature. So what are the possible application of phase changing materials? So what are the possible applications? Possible applications. So the possible applications of phase changing materials can be in solar energy systems, solar energy systems, that is photovoltaic cells, and also insulating effects in buildings. We can have application in electronic devices, electronic devices, in healthcare and medical systems, in healthcare and medical systems, in smart textiles, in smart textiles, and in building envelopes for insulating effect in buildings, in building envelopes. Now, let's talk about the confinement of molten PCMs. Confinement of molten PCMs. So basically, the main purpose of confinement is because if we don't contain the PCM, it will leak out and it will reduce the efficiency of our system. So basically, we have three types of confinement. Three types of confinement. So first one is box confinement. Box confinement. Second one is micro to macro encapsulation. And the third one is form instability. Form instability. We will discuss this one by one. So let's talk about the box confinement first. So we have said that as we have transitioned from solid to liquid, we should be able to confine that liquid. So we should be able to confine the liquid, and for this one, we can take it as an example of thermal exchanger, thermal heat exchanger basically. So we have something like this, and okay, something like this. Okay. So here it's coolant in, coolant out, and we have fins here. So this is an example of thermal heat exchanger. So this gray part, like in this fins, we have filled with the PCM material. So we are adding PCM material to absorb the heat. Now let's talk about the macro encapsulation. So we can think to have encapsulation, which means that we have a core of a PCM material surrounded by a different cell protecting it from the environment. So basically, we have a here core of our PCM material, core of PCM material, and it's protected by a shell. This is the shell, which protects the core of the PCM material from the outside environment. So we can maximize the surface to volume ratio. We can maximize the surface to volume ratio. And so we can have different granules of our PCM material, and we can think to store them inside a tube where we have a flow of our steam. Now let's move to the third type of confinement, that is form stability. Form stability. So in this case, we are adding something to our PCM material. So in this case, we are adding something to our PCM material. So what is this something to our PCM material? Which helps to retain their shape. Which helps to retain their shape. So what is this something? So this something can be gelators, inorganic fillers, or ceramic particles. So we can have interaction between the PCM and the confinement, and we need to take into account which materials we are using. So if we have an alloy PCM, basically aluminum, silicon, copper, or iron, which is embedded in steel or shell, which is embedded in steel as shell, then iron and aluminum interact quite a lot. That is, they have good affinity. So when we have melting of alloy PCM, we have interaction between the liquid alloy and iron, and we end up with thickening of iron layer, and we can change the composition of aluminum, silicon, copper alloy. So basically, what implies the change in our composition? So by changing the composition, we change properties, we change the melting temperature and enthalpy of fusion. So this is basically a problem we are going to face when we have an interaction of the PCM with our shell. So okay, so this is for this lecture. Thank you.